All right, let's clean up the desktop here. And all right, so some information so that if you're watching this from YouTube, you'll know who it is. My name is Han-Sang Bae. I'm the CTO for Riverbed. But for this session, I'm basically a packet head like everybody else here. Okay? It's been a passion of mine for a very, very long time. And I always start my Wireshark or Sharkfest session this way. And I don't even really remember how I got started from the very first Sharkfest. And I believe this is the t-shirt from the very first Sharkfest. It doesn't have a year, and Jim says it is, so I'm going to go with him. And it makes sense because it doesn't have Sharkfest 28 or 20, whatever it was, 2008, whatever. So I'm assuming this is the very first one, and Jim says it is. It's good authority. So I've been doing this a long time. And I always start out by saying that there is no way I can teach you packet analysis in an hour and a half, not even a full day, probably not even a full week. I can, however, give you tips and techniques on how people do this. And so there are all other instructors here who do very, very good job, great job of explaining how to do packet analysis. Different flavors, different methodologies, they're all valid. Mine is more valid, okay? And I stress that not because I'm Ron Burgundy, I'm kind of a big deal here moment. It's not. It's whatever your method is, stick with it. Because you need that constant picture to make sense of it very, very quickly. If you change things around, I am lost. If I were to use Chris's, or Jasper or Christian's or anybody else's, Sake's for example, I would be a babbling idiot because I would not know what the fields represent, and my eyes are trained in a certain way. Okay, so my way or the highway applies in packet analysis. Okay, make sense? So you can Google my YouTube page, and you'll see the previous Sharkfest sessions there, including this one, and hopefully I'll have it up tonight. Like I said, it's a personal challenge. The other one is I will get back onto Wireshark because I've not been part of it because, and here's why. I'll be very honest with you, and I'll get started with packet analysis in just a second. The format with Ask is that if I ask a question, I don't want to leave anybody hanging, right, if there's a follow-up, etc. But unless I subscribe to the email alert, I sometimes forget what it is that I was talking about, or which thread or which question, etc. So then I feel kind of guilty that, and then the other, in order to not do that, I have to then go through every single question again and again and again. At the same time, I don't like a bunch of emails coming to me, so I'm caught between, rock and a hard place. But I will make more time to go there because I realized something, and this was kind of a moment of clarity, that another passion of mine, I'm not connected to the internet, is DCS, which is a flight simulator. It's an incredible flight simulator. And I noticed that I had 5,000 posts there. So I thought, they're both passion of mine, flight simulator, VR, and packet analyzer or packet analysis. I thought, if I can post 5,000 on a flight simulator forum, I can certainly get back onto Ask, even if it means reading every question. So I'll start to do that, all right? Okay, so my sessions typically are, so that's the end of that's all you need to know from them. We'll jump right into the packet analysis piece. And this was just a sample trace file that I wanted. So these are all the stuff that we're going to look at today. And you'll see the list of Sharkfests here that I presented at, which is kind of cool. So the first thing is compilation of things that I went, that's interesting. And I have here, and it's not Firefox, it's just any browser these days, right? So take a moment when you get back home and see what your browsers are doing, okay? Because I think you'll find that it's pretty interesting. So for some reason, this is stuck on DNS. Not sure why. I can find a bug, I guess. Okay, that's interesting. So I'll go back to here. Oh, maybe it's not. Okay, I did just filter for DNS. That's fine. So let's go to DNS view here then. Interesting. Gerald here? Help, little help, little help. Did I clear the filter? Did I not clear the filter? Okay, I'll do that. Sorry. All right. So, so this is, I just, again, curious, right? So another advice that I can give you is wherever you go, do a packet capture just to see what's going on, okay? Remember that old saying in packet analysis, and if it's not, it should be. If the first time you look at a packet trace is when something's going wrong, you don't have a baseline, okay? So you need to be curious and constantly capture. Here's what I did for, I opened up my browser and I just captured. I did nothing with the browser. I have the toolbars, I have the icons, and you can see it going to Akamai, you can see it going to Mozilla, you can go into some push service, auto push. You have, I don't know what that is. A lot of these I actually did. There's incoming telemetry from Mozilla because I signed up and said, yeah, I want to send feedback, right? Some Twitter stuff. And I don't know why it's going to Twitter because I don't have any link to Twitter on my browser, but it's going there anyway. There's OCSP, that's good. That's, checking for revocation for certificate. Google Analysis, this one, I don't know, I should look it up. Windows.net. So total 153 DNS Q&A was asked just by opening a browser, which is kind of scary and not scary at the same time because bandwidth is cheap, right? And I have a gigabit service at home and I love it, but it's also something that every once in a while, just do a packet capture, okay? Because at the very least, you'll get maybe an aha moment and you can solve things at home with packet analysis, right? I'll prove it to you right now. So these are just compilation of things that made me go, and as like my wife used to typically says, how are normal people supposed to figure this stuff out? I'll give you an example. So I couldn't connect to a printer, and I didn't know why. I kept struggling and struggling and struggling, and I was like, this, POS and this and that, and it's not working, and I'm pinging, and I'm doing the normal stuff of a troubleshooter. I can ping, but I can't connect to the printer. So this is, brand new printer, and I have an application that goes with that printer for scanning and faxing. It's a multi-function. And so I did a packet capture. Why am I not able to connect? I can ping, which means I have layer 3 connectivity, which means ARP is good, right? So I've already ruled out a huge classes of problem. ARP is good. There's no DNS involved here because it's just using IP address, and layer 3 is good. So clearly it must be layer 4, and I wanted to know why. And look at packet number 3. This is all I needed to know on why I couldn't connect. Because being the control freak that I am, I went to the printer setting and said, don't need you, don't need you, don't need you, don't need you. And one of the ones that I turned off was service location, all right? And this application apparently uses that to find the printer, which makes perfect sense because that's what this SLP is all about, okay? And you can see here that you immediately get a UDP and an ICMP message that says destination port unreachable. So this is a printer saying, hey, idiot, you shut down the port, so I can't answer you, and therefore I wasn't connecting. Okay, now, this was self-inflicted wound because but I don't like printers spewing everything because I don't have everything at home. I don't have Apple Talk anymore. I don't need all these other ports that are open, okay? So this is an example of Wireshark can help you in everyday example. But it does bring up an interesting point. When you're troubleshooting in your mind, you need to frame a picture. You can't we're way past the ability for any analyst to open up a trace file with no guidance, with no hint of where the problem is and start going through. Sometimes you get lucky, but most of the time you're not. Because do the math on gigabit, 10 gigabit, 100 gigabit, 400 gigabits right around the corner. You cannot consume that much information, figure it out. I don't know who you are. I don't care who you are, okay? Now, if you're like Jasper and Christian, you write a bunch of scripts and T-Shark and et cetera to offline analysis, find points of interest, and zoom into that. That's another technique. And there's a webinar coming up where Graham and Saki and Jasper and Christian are going to host where they talk about command line tools. Okay, so be on the lookout for that webinar because command line tools will help you save the day. Excuse me. when, when so much data is at stake and you have to analyze, okay? So again, the point of this was, yes, I solved my printer problem, but really, just by looking at this, I was able to figure out layer 2, layer 3, good, move on. Okay? So quick and easy, right? We're just getting our feet wet. Then let's look at another issue where, which one should I look at? Okay, so here's one. It's a different printer. I have a lot of printer problems apparently. I don't know why. And this was an example of, so we have multiple computers at home. Obviously, I have my computer, my kids have Mac, my other son has Mac, and then my wife has a ThinkPad, etc. Probably like most of your families, right? Not to mention all the mobile devices. And 3 of the PCs and laptops, Mac and Windows, could connect to this printer. The other one could not. Same OS, same Mac. One can connect, the other one cannot. And I said, what the hell? Why is it doing that? So I did a packet capture, right? Because any serious problem can be resolved through the use of superior firepower or packet analysis. That's the mantra, all right? So, dot 21 is the printer, okay? And I think 235 might be the one that's trying to connect. It doesn't even matter, but you'll see here something interesting happening, okay? And it's TCP, and so I can ping, I can connect to the web interface. I believe that's the use case here. But I can't connect the printer to the print server, all right? And without going into a big gory detail on how I solved this problem, you see the huge delta. So I do my usual workflow, right? I look for delta, I come down here, and it's like, wow, there's huge deltas here. And I'm banging on the keyboard, so this is not user-driven delay whatsoever. So why is there a big delay here? And you'll notice here that there's an ARP protocol here, and it's looking for .21. Someone's looking for .21, right? Which is printer that I'm trying to connect to, okay? So this led me to thinking, all right, I see the ARP request there. Okay, so let's put this back in order. And in fact, let's just look at ARP here. So here's one. It's an ARP request. And here's an ARP request. Here's an ARP request. Here's an ARP request. Here's an ARP request. What am I missing? Reply. Okay? So that's all it took for me to realize that, oh, I have a TCAM issue. Okay? Or TCAM is tertiary content addressable memory. It's where most devices keep things like ARP and multicast, NAT addresses, star comma G for multicast, things like that. And this is a simple consumer device, okay? And for whatever reason, this one IP address got stuck and it wouldn't refresh. So it held on to this MAC address of other laptops just fine. It just couldn't do it for my one MAC address, the Mac computer that I was trying to connect to. Okay, so how did I solve this? Yeah, exactly, three finger salute. I unplugged and plugged it in, and it was fine. Now, so this brings me back to that. How would normal people solve it? I don't know. Maybe they call tech support, and tech support will say, try turning it off. Or do you have the latest download, patch level, can you ping, etc. But here, even when you just ping, it's not going to work, right? Because the layer 2 isn't working. So the idea here is, again, very, very quickly with the layer 2 not working because I can't ping, I was able to reduce the problem domain. Okay, this is the key. All I'm trying to tell you is that think about the problem, quantify it, and reduce that domain so you don't have to go troubleshooting everything all at once. Okay? Limit yourself to layer 2. Make sure you rule that out. Limit yourself to layer 3. Make sure you rule that out. Okay? And then get to layer 4, which is TCP. Does that make sense? Too often we jump to the most exciting part, and we get stuck because we never ruled out the usual suspects of layer 1, layer 2, and layer 3. And these days, layer 1, for the most part, they're all good quality cables. You don't have to worry about it. And chances are you're not going to see it anyway. Okay? Most even consumer devices throw that out. So unless you have a physical tap, you're not going to see layer 1 problems. Okay? So just a quick tip on making sure you visualize a problem, contain it, and start from layer 2, layer 3, and move up. Because you can rule those out very, very quickly, like I did here. All right? Yeah, I know it's not very sexy, but I wanted to give you the examples of how to get started. Okay? All right. Another one. This is just an example of so my older one does debate, and there was a national tournament in Florida, and there was live streaming. So of course my wife wanted to see the live streaming, and no problem, and all of a sudden it stopped. I'm like, what the hell? Why did it stop? So again, going back to, I don't know how normal people would solve these problems, but I wanted to rule out things. Why did the live stream stop? I had a suspicion because it's the finals and maybe it's the demand. And I just did a packet capture while I was doing live streaming. The first thing I do is let's look at DNS. And there's a bunch of stuff happening here. And right there, speechanddebate.org is 8.40 something. Okay, so right away I know DNS is working. Remember, every application starts with DNS. Don't forget that. Okay, every application starts with DNS. So don't rule that out when you're troubleshooting, because it could be as simple as DNS query not working. The other thing is, when you capture, you must include ICMP. Okay? When you capture, you must, whatever BPF filter you use, put big parentheses around it and add or ICMP. And you'll see why in just a second, but random routers along the network will send you an ICMP message about administratively prohibited because there's an access list, PathMQ discovery, and it may be coming from a source that you don't expect, okay? So if you're capturing from your machine, of course it's coming to your machine, so it's okay, but if you're capturing off to the side, you may not see that message, that ICMP message. All right, so make sure you capture ICMP. I mean, you can filter that out very, very quickly, right? And all it was so I just needed to know the 8.40. So the next thing I can do is I can go to be lazy and just do IP.eder equal 8.0. You don't even have to do all of this, but okay. And what do you see? All you're seeing here is, if I open it up, SYN, retransmission, retransmission, SYN, retransmission, retransmission. What happened? The server is so busy, I come knocking on the door and it can't answer. That's it, case closed. You don't have to worry about your flash, you don't have to worry about your browser, you don't have to worry about your network, you don't have to do anything. This is just a server that's so under duress that it can't keep up with just even a connection open. Okay? You can stop your troubleshooting here. Because otherwise, you would have been doing things like F5, flash update, or browser update. Let me try Chrome. If you're like me, you have multiple browsers, right? Because you need to test. So I use Firefox, I use Chrome, I use Edge. Edge actually, you may laugh at me, but Edge is actually a pretty damn good browser now. It really is. And so I find myself using Edge more and more, but I know you'll throw things at me, but to me, so my go-to, because muscle memory is Firefox, then I do Edge, and then I do Chrome in that order, typically, okay? So again, very, very quick troubleshooting tip on problem isolation, okay? All right, so let's move on to something a little bit more interesting. And this is, let's see, which one should I do? I think I'm going to do this one. All right, so this is a typical user is slow, things are slow, it's intermittent, it's annoying. And I need to adjust my columns here because this is, bear with me, and I can do automatic adjust here somewhere. There it is. Okay. So I'm not going to go into the basics of TCP, but you need to be able to do sequence number analysis, right? That's the first thing you need to understand. But let me just take a moment on TCP so that everybody has the baseline of what it is that I'm talking about. So we understand the importance of doing sequence number analysis. This has 2 shark fins in it, so I'm not going to go into the individual what is, but I do want to set the big picture. So TCP sends data, doesn't packetize data, doesn't care about packetizing data. It's not TCP's job, okay? Underlying protocols do it. TCP's job is to send data. All it is grabbing a giant hose between 2 source and destination, and you stream data. That's it. That's why the textbook definition is stream-oriented, connection-oriented. There's your hookup of the hose, right? And it's stream. There is no beginning and end to TCP data. There's a beginning TCP open. There's a fin wait, close wait, fin wait, all that. That's just the, think of it as connecting the hose and disconnecting the hose. Outside of that, there is no source and destination. Theoretically, you can keep a TCP socket open for 10 years and never send a byte. Obviously, modern OSs detect that and will start to do things like keep alive. Are you there? Okay? So remember that when you're doing, don't get wrapped up in the packets, the size of the packet, although it's important, and I'll show you why in just a second. Just keep in mind how TCP sends data. There's no beginning, there's no end. Then there's another thing that you need to be aware of, and that is applications with internal buffers. And this is something that you can pick up, and I'll show you how to pick that up in just a second. And it's actually very, very damaging to throughput. So what I mean by the application buffer is application is dictating how much data it's going to give to TCP. In other words, what bucket size am I going to use to dump the water into my hose? Ideally, ideally, you want that bucket to be massive. So you can constantly pour the water into the hose so that the hose, the bigger the hose, the thicker the hose, the more water it's going to move, okay? And that's the bandwidth window. That's how it all comes into play there. But most applications will have buffer, and it will only use a small bucket size, okay? Because it's old, it's trying to do things like when TCP was doing congestion control and back off, and we had limited bandwidth, et cetera. Even today on the modern internet, obviously we don't have limitless bandwidth. So TCP looks for feedback and then slows down, et cetera. But the application buffer size is, I'm not going to go so far as to say it's insidious, but it's actually bad for performance. And it's easy to pick up. And there's actually an article here that I want to show you, and I'll post this as well. And this is actually pretty old, right? So so here's a paper from what date is this? There's a date in here somewhere, but that talks about performance of TCP, and section 3.1 is buffer tearing. Okay, and if you look at that example there, I'll walk you through it real quick. So here's a buffer size of 4096. This is not a TCP window size. This is application buffer size. This is application's bucket, okay? It's willing to give you 4096 bytes of data into TCP, and that's it. Okay? So what does TCP do? Well, TCP says, no problem, I'll send the data, but TCP cheats by looking at the MTU and calculating the MSS. Okay? So while I said, TCP's job is not to packetize, TCP cheats by looking and saying, hey, how big is your MTU? I'll subtract my header, and there's my MSS. So 1460, you can tell the age of this because modern day OS with the Windows scaling and SAC and everything, 1460 is typically not the MSS anymore, okay, maximum segment size. But what this example is showing there in the parentheses there is that 1460, that's 2 packets. The remainder you have is 1176, and then you have that remaining 4 bytes, okay, to fit that 4096. So for the first two, 1460, 1460, that's awesome. You get an immediate acknowledgement back. And this article actually has one thing that I would argue with. And it says there that in the thing here, if Apache sends a message a length of 4,100 bytes, the first 4096, because you're sending 4,100, the buffer size is 4096, so TCP has nothing it can do other than send 1460, 1460. And then 1176, and then remaining 4 bytes are then buffered to be sent. The 1176 byte is not delayed because the first 2 full-size segment was immediately acknowledged. You see that sentence there? Okay, right? I'm gonna move it up a little bit. So look at that parentheses 1460. I should use this part right here. Okay. So concentrate on this part right here when I zoom in. So the problem is that it says the first 2 packets are immediately acknowledged, which is true. But what if it's not local? You have to wait for that acknowledgement to come back. So there's that problem. But the real problem here is that the 1176 is a non-full MSS, and it's not even 2 of them. Remember the rule, Microsoft is any 2 packets I acknowledge immediately, but if it's Unix or Linux or variant, it needs to be 2 full MSS before I acknowledge, which means we hit that classic Nagel delayed act, right? I sent you 1 small packet of 1176, so I have a couple more bytes left over, but I can't send it to you because you haven't acknowledged it. So we waste a round trip. Does that make sense? Okay, so this is why buffer tearing, and you can read through this, and I have, in previous Sharkfest, I went through ad nauseum on why Nagel delayed act to this day can cause you problems because of buffer tearing. Okay, and we'll see some examples of that today. All right, make sense? Okay, if you don't know what the hell I'm talking about right now, that's okay. Just Google's your friend, look for delayed act, Nagel delayed act interaction, or just type Nagel delayed act, and you're going to see, you know, a mountain of data on why that's bad. All right. So let's go back to an example trace file here. This one may or may not be that, but the first thing I do is I scroll down. I just have it, and I'm just observing, and I'm looking for patterns, and I see some, you know, some interesting things because I see this. The double here, some stuff here, and single here. And every time I see double, it can mean a good thing, meaning it means that it could be that it sent 2 full packets or 2 packets. So that's a good sign. I don't know if that's the case or not. I'm just saying I'm visually looking at looking at patterns. There is something else that's concerning a little bit, and that is this little guy here, right? So I'm looking at even numbers of packet, and every time I see this pattern, full, 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 small, I'm a little concerned. Because this is exactly the use case where the buffer tearing can hurt you. Okay? So here, if you look at this guy, all right, so I actually have an acknowledgement 4 here that says which packet I'm acknowledging. So this guy's acknowledging packet 887, this guy here. That's good. That means these packets came down, and this 200 says, yep, I'm good. You can check it 2 ways. You can create an acknowledgement 4, or normally there's a little checkbox here that says it's acknowledging this, but we know that it's acknowledging packet 887. The other way we can check is looking at the 672125. I'm sorry, let me make this a little bit bigger. Here is the last byte, so sequence number is going from 234 to 821, and the acknowledgement number of this guy is not, 887, I'm sorry. This I was like, another bug, now it's user error. So the acknowledgement number here is 672125, and it should match the next expected sequence number. It's acknowledging 887, I'm off by 10 here. So it's up here somewhere, okay? So let's scroll up here, and you can see 887. There's my little check mark that Wireshark shows you saying, notice when I clicked on this acknowledgement, a little checkbox showed up here that says, this is what it's acknowledging. little UI enhancement, but because I'm used to not having this back in the days, I have a column here for acknowledgement, which packet is acknowledging, all right? But the point is that whenever I see 14 here, 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 I get concerned because if I'm sending to a Unix server, this is going to cause me issues. Why? Because these two will get immediately acknowledged. This one and this one for Windows will get immediately acknowledged, but for Unix, you may not. Okay? So this is a good example of buffer tearing that could come into play. Does that make sense? Okay? Things to look for. I actually have another column here that I removed called bytes in flight. I use that. And how many bytes I have from the last push. Okay? And so I think Kerry, he has got a session, but he created, and I cover this in webinar, so if you look at if you Google search or look at my YouTube page, I went through these in detail. Okay, so that's what I was doing when I was scrolling down. Okay, these are the things that I'm picking up. The other thing that I do is I look for TCP analysis flags. I just want to see what I'm up against, and looks like I may have packet loss here. I can see a retransmission and some dupacks and a fast retransmission. Okay, so I had packet loss. But in the big scheme of things, it's not that many. I'm not going to worry about it, especially considering it's a fast retransmission here that Wireshark identified. Okay? So when you have a fast retransmission, you lose almost nothing in terms of throughput, because fast retransmission is nothing more than the receiver of the data saying, I lost a packet, or packet didn't come in, packet didn't come in, packet didn't come in, and then the next one triggers the sender to immediately retransmit without slowing down. Okay? Back in the days when you had retransmission, TCP used to throw everything out from that moment of packet loss. So imagine a packet train of 10 leaving. So 10 packets worth of data left the station, packet number 5 went missing. Okay? And the receiver got 6, 7, 8, 9, 10, but it missed 5. Back in the days, it had to start from 5, throw out 6, 7, 8, 9, 10 packets worth of data and say, start over, which is stupid because we know that the receiver received it. And so TCP enhancements with selective acknowledgement, et cetera, covers that, okay? And the new TCP sec says, I have a hole, but don't worry about retransmitting all this trailing stuff, just give me that missing hole. And because there's feedback of more packets coming, and I tell you immediately, hey, don't even try to guess at this. There was a packet loss. Retransmit right now. Don't wait for any timeouts. Again, in Singapore session, there was, if you go to a retrospective page of Wireshark from 2018 Singapore, there were great classes on what selective acknowledgement, how it works in gory detail. Okay? So if you really, really want to know and understand how selective acknowledgements work, look at that session from Singapore. Okay, and you'll be able to find it by looking at the course description. If not, email me, and I can point you to the right location. Or on the YouTube, if I remember, note to self, I'll post the video that covers that section. All right. So packet loss, I'm not concerned about. The next thing I do is I look at the delta, and I scroll down and I see, wow, there's a big delta there. So this is delta time is displayed column, and I always do this. I go to the highest delta, and I start there, because the highest delta between packets means probably the biggest pain point, because somebody was waiting, right? Reasonable. It's not always 100%, especially not if it's user think time delay, like I'm sitting here looking at a screen before I hit OK. It'll show up as delta. Wireshark, from a packet perspective, doesn't understand if it's a user delay or system delay. Okay? There are some techniques on trying to decipher that, but it can get a little tricky. So, be that as it may, I come over here and I start from here. Okay? And the first thing you'd want to do is rule out missing packets, rule out retransmissions, etc. If you were paying attention with TCP Analysis Flags, it might have pointed one of these as problem child, okay? But because remember, my way is the highway, my method's the best method. I have a systematic way of doing things because I don't want to miss something, so I always revert back to doing sequence number analysis, okay? And sequence number analysis is nothing more than this guy acknowledged packet number 1941. So from 10 dot perspective to 200, I'm all caught up, okay? So 10.10 dot sent something at some point in time, and 200 dot is saying, hey, you're good up to packet 1941. This guy sent 157 bytes of data, 200 to 10.10.10. And you'll notice here that about 186 milliseconds later, the 10.10 guy acknowledged it. Okay? With me so far? Okay. All right. Then this guy had some data to send, 232 milliseconds later, and sent 76 bytes later. I'm sorry, sent 76 bytes of data. So what was the delay between here and here? Okay, it could be Nagel delay, it could be application delay, it could be a bunch of different things. I'm not going to go into it now because I actually did go into this in detail. But for now, let me get to the part that I'm concerned about, which is identifying this guy. All right, so I see here that 200.200 sent an acknowledgement up to this point. Okay, then this guy, this is the moment where we had the 3.5 second delay, 3.75 second delay. So at this point, am I all caught up in my conversation? Are there any outstanding data in both directions? TCP is a duplex, meaning I can send and receive at the same time. What you have to rule out is somebody holding on to the data and didn't answer? Why? Because that almost always means application level delay. In other words, if I sent you some amount of data and I didn't hear back from you for a long time, then it's an application holding on, thinking about it, or it's the user reading something and clicking on OK or next. Okay? So this is why you have to investigate, query, look at ask the user about, or if you can, watch how the application works. Sometimes you have the luxury, sometimes you don't. But the more you do this, you can kind of discern almost through sixth sense and through experience whether this is user delay or system delay. Okay? System delays tend to be, anyway, I'm not going to go off on a tangent there. So the main point here is that 200 to 10, everything's been sent. 10 to 200, everything's been sent and acknowledged. So this delay of 3.75 seconds is on who? Is it on 192.168.10.10 or is it 200.200? 200.200. Okay? In other words, let me repeat that. Up here, if you do the sequence number analysis, you will see that 10.10 sent something to this guy, and it was all acknowledged by packet number 1946. The 200.200 sent something to 10.10, everything was caught up until this moment in time. There are no outstanding data on the wire, but this guy starts new conversation, new data saying, hey, here's 137 bytes of data, do something with it. So the question is, why? Why did this guy wait 3.7 seconds? Is it a system delay, like I said? Is it the 200.200? Right now, it looks like it's 200.200, right? It's an application level delay. Does that make sense? So with the evidence that I have, it's an application level delay because everything is all caught up to here, but right at this point, 3.75 seconds later, the 200.200 decides to send something else. So I said, oh, it's an application delay. Turns out it's not. Okay, I use some other techniques I won't get into. So like, that's interesting. So if that's not an application level delay, what else could slow down layer 3 or layer 4 conversation? I ruled out that 200.200 is not. Okay? So one thing that we can look at, we do have the luxury of looking at, is the IP ID. Okay? Because IP ID is sequential or it increments by 2. Or it's all 0. Okay, so it's just a luxury. You do not need IP ID at all unless you fragment the packet. That's the only time you need IP ID. So the IP identification, which is 64 bytes anyway, 64,000, it may be used, it may not be used, or it may increment by 2, it may be all zeros. So the reason why I do look at IP ID field is because here is 15804, and this guy is 15814. What does that tell you? He was talking to somebody else. Remember, there's only one IP stack, multiple TCP conversations. Okay? TCP operates at the socket level. Source destination IP address, yes, but there's also a source destination port. That all goes through the same IP stack. Okay? And the best way to visualize this is if you ever been on a road where they have toll collectors, imagine a toll collector, not Easy Pass or Fast Pass, but a human toll collector, where you have to exchange money. Imagine having a toll collect. It's a 4-lane highway, but the toll collection happens through one booth. So the 4 lanes are your TCP applications, browser, email, another browser. Having application issue here. So it's resyncing, I guess. One of the screens is going to resync. So imagine 4 lanes of highway. Those are independent TCP conversations, but one toll collector. And every time you pay your toll, you get a receipt with a sequential number stamped on it, and that's your IP ID. Okay? So by looking at this, I realized that there were other conversations happening because it went from 804 to 814. If I come up to here, 15796 and 15803. So yeah, 1.3 seconds is an eternity. He's talking to somebody else who, I don't know, maybe it's some other conversation, but it said, why didn't I see it? If I know he's talking to somebody else, why didn't I see that conversation? Let me repeat that, because these questions all matter. And this is what you have to do as an analyst. Think about all these different things, some of it through experience, some of it through classes like this, and you have to always ask yourself, what does that really mean? If I'm capturing at 200.200, let's assume for the moment that I am, and I know for a fact that between this conversation, this packet and this packet, this 200.200 had other conversations going on, why don't I see it? Yeah, so the answer that we got from the audience was there must have been a filter. Okay? Right? It's reasonable. So I asked, did you have a filter? Yeah. Was it restrictive? Yeah. Okay. Open it up. Because I'm curious what's happening between here and here. So they did. And that trace looks like this. So same thing. Go back, go down to delta delay. And what's the one thing that you immediately see? Sorry. For those of you listening to YouTube and just blew your eardrums out, I hit the microphone and dropped it on the floor. So immediately you see what? ARP. Interesting. Is it things that I care about? Okay. Do I care about this ARP? Because there's ARP happening all the time. Don't just look at the ARP and say, oh, wait a minute, this is ARP. Hansang talked about ARP. No, it's not always because ARP is happening. It's part of your life. But there is something interesting here that caught my eye, and that is .1 address. Okay? Like most people, most network engineers, you probably use .1, .2 as the physical, .3, .4 as the HSRP, VRRP, or the reverse. .1, .2 as VRRP, HSRP, 3 and 4 as a physical, or you may use the upper level. I don't, like 254, 253, etc. Again, standard is standards, and that's fine. But what caught my eye was there was actually a lot of interaction for ARP right at that latest another delay, and it involved a bunch of .1, .2, people looking for .1, .2. okay, and getting different MAC addresses, etc. People were getting confused on ARP table with .1 and .2 HSRP MAC address. Why? Because it was misconfigured. Okay, so this was a change that occurred. Someone messed up the HSRP address, and every once in a while the ARP, because remember the ARP timer and the switch TCAM timers are different. All right, so sometimes it would work, sometimes it would lose its mind, sometimes it's a race condition, and I get the right ARP, everything is going, and all of a sudden I lose my mind, I start ARPing, there's a lot of confusion, and I get, oh, okay, there you are, and the conversation continues. Okay, does that make sense? So the fact that this was an ARP problem takes experience to root out, and I've done this session before, and I go into details. What I wanted to show you was a thinking process that happens almost subconsciously that led me to this trace. That's more important, because if you didn't think that through, of that 200.200, 2 packets back to back, everything's caught up, everybody's done talking, everybody's acknowledged everybody, and yet the IP ID is different, means very reasonably that there was a filter, and you may be missing something. And that's when you start to open up. So this is a philosophy of packet capture. Some like to capture everything and filter later. That's a good, because you can't miss it if you capture everything. But the downside to that is a simple math problem. TCP is duplex. Switches are duplex. When you capture, you're capturing gigabit transmit, gigabit receive. But you span it to a gigabit interface, okay? Which means you're sending potentially 2 gigabits worth of trace to a 1 gigabit port. Now the answer is simple, get a 10 gig card. But those cost money. Taps cost money, okay? So this is where experience comes in. Observe the traffic. If it looks like it's gonna fit within, because it's never full wire rate transmit and full wire rate transmit this and that, right? It's not. Agreed? Okay, so you can observe it and say, yeah, I can reasonably conclude that transmit and receive will fit into one span port and it'll be okay. And if there is fake packet loss, you'll be able to rule that out very, very quickly. What's a fake packet loss? Fake packet loss is where the sniffer or the Wireshark, your capture device, drops the packet, or the switch overruns and drops packet, but in the real world, there was no packet loss. You can spot that because Wireshark will tell you previous segment not captured, right? Because it knows there's a gap in sequence number. There's no magic behind this. It's just a dissector that says, hey, wait a minute, sequence number 1 to 10, 10 to 11, 20, 20 to 30, 30 to 40, 100 to 110. Oh, previous segment not captured. It could be because packet loss, or it could be a fake packet loss. If it's real packet loss, what are you going to see symptomatically after that chunk of data that's missing? Dupacks, right? You're going to see triple dupes. You're going to see dupac 1, dupac 2, dupac 3. Or you're going to see for sure retransmissions. Okay? Make sense? Okay, so the goal of this trace file was from the previous session, where realizing that there were other conversations happening between 200.200 is what led me to ask the question, did you have a filter? Yes, I did. Open it up, and we were able to find root cause. Okay? Again, reducing the problem domain, slicing and dicing to get to the right root cause. Any questions? No? Okay, so I'm going to go back to another example, just a random example here. And I have until 11, I believe, so we have plenty of time. This is my, DCS, the flight sim that I had. And for some reason, so Forum is all mostly text-based, and it's a little slow, but hey, it's in Russia. It's all the way, it's hosted in Russia. It's a Russian company. So I expect some level of delay, and it's okay. But every time I would download a picture, I couldn't get it, right? It took a long time. And I'm a patient person, so I'm like, yeah, it's the server's delayed. I'm a network guy, so I immediately jumped to it, blaming the application. And then I realized something. When I was flying United, I was able to download those pictures. And I went, what the hell? She was like, what the hell? You can download faster on an airplane with a LEO, low Earth orbit satellite involved with that latency? Like, what the hell? So I filed it away, and then I realized at the hotel, which is mostly congested, I could download it. So, and I uninstalled browsers because Edge was doing it, and Chrome was doing it, and Firefox was doing it, and so I immediately ruled out me, my computer, etc. And then I happened to be on United, and I looked it up, and sure enough, the pictures came up, albeit slowly, but it came up. At home, it would take a long time. So I did a packet capture, right? Like any packet head would do. And you can see all the, you can jump to DNS, and you see all the, by the way, this is kind of like their Facebook or ad stuff, so I kind of say, man, you guys are doing a lot of advertising, and so you see a lot of that. But hey, it's a free forum, and that's the price of free. And then I looked at other things, and if I do this, Tcp Analysis Flags, you can see that there's a lot of retransmissions, and these are real. How do I know they're real? Because I see DUPAC 1, 2, 3 retransmissions. There's a bunch of different retransmissions. So these are packet loss, a lot of packet loss, okay? If you look down here, and you zoom in down here, you see that out of 400, 132 were duplicate acts and retransmissions. Okay? So it's not that there's 33% packet loss, because one packet loss could have 4 or 5 packets, right? Triple dupes and the retransmission itself. Even though this is small, so even if you account for that, that's a huge number. But it only happened at my house. That's, again, the aha moment. You think, there's a saying in Korea, even a monkey falls off a tree every once in a while. So I don't know why it took me so long and why I just stuck with it until the United moment. What's between me and this server in my house? Because clearly, on United flight it works, at a hotel it works, my house it doesn't. So the problem domain is my house. It's not my browser, it's not my kids, because I use the Mac and etc. So the problem is my house. I rebooted the cable modem, but I'm pretty sure it wasn't the cable modem, because other traffic, weren't having problems, or were they? Did people just get used to what they got used to? I don't know. Then I realized I'm troubleshooting. My kids aren't complaining, but they, for the most part, work in their bedroom upstairs for homework. I'm downstairs in my work. So what's different about those two locations? Wi-Fi. Okay? And I didn't have a PCAP card, the PCAP card, so that I can look at the wireless stuff, but I didn't need to, because this wasn't a cable modem problem, this was a Wi-Fi problem. So my Wi-Fi, that particular antenna was POS, it was crap. I turn it off, put in a new one, problem disappeared. Okay? So if you really wanted to troubleshoot this, you can look at the control frames and the beaconing and everything else, and you can geek out and look at that. I'm not a wireless guy, so I wouldn't have been able to troubleshoot that anyway, but I suppose I could have went to ask Wireshark.org and say, hey, can you help me look at this? But this, again, was a methodical troubleshooting, albeit a little late, that led me to problem isolate by using just common sense. That's the point I'm trying to make here. Don't just go straight to packets. Logically separate out problems so you can discern where the root cause, the domain is, and troubleshoot that way. Okay? And this was actually a pretty pricey cable provider that advertises awesome wireless. and turns out it was crap. Okay? Any questions about this? I know there's nothing exciting from a packet analysis standpoint, but I'm just giving you philosophy of troubleshooting and problem domain isolation. Okay? Make sense? All right. And you're probably thinking, man, Hassan, you must have a lot of problems at home. I kind of do, maybe I don't know. Sometimes you just get used to what you get used to. And so let's look at another example where I'm doing an Amazon upload. This is a while ago. And this is, why wasn't it faster, right? Amazon is practically has limitless bandwidth. And I'm uploading something. You can see port 80 here, and you can see Sin Synac. So again, I do my usual thing, scroll down, and right away I'm already like, that's kind of interesting, okay? Because I'm looking for patterns on the length. And I like, when I scroll down like this, I like to see changes that don't happen too much, okay? I like to see same numbers appear again and again, and I don't. You can see that squiggliness by looking at the column data. That's what I'm really looking at. I'm looking at, there was a big delta that I just flashed by, okay? So if I scroll back up here, you're gonna see this, okay? Why? Because my brain was tuned to a bunch of zeros, and every time it squiggles, I just stop and look, okay? Again, it only comes with experience. And there's another script. The other thing that was interesting is on the right-hand side, there's an awful lot of pushes, right? So this is one of the ways you can detect buffer tearing, where the application flushes the buffer and it slaps a push bit on it. And when you're doing bulk transfers, you don't see push bit. So you're going to see, in this case, the maximum segment size looks to be 1340. So it's 1340, 1340, 1340, 1340, 1340, the little remainder guy with a push bit. But here's something interesting. It's not. Every one has a push bit set on it. So it's a little bit different than a normal TCP application. Okay? In a normal TCP application, you would see a full-size packets, a string of them, would not have a push bit until someone flushed the buffer and set that push bit. Okay? Make sense? So why didn't I get good throughput here? So let's start doing some troubleshooting. Okay? The first thing is I sort by delta, and I go all the way down. Here's a 190 millisecond delay, and I see that it's a naked ACK, meaning that I am not sending any data, and it's just an acknowledgement. So as soon as I see numbers like something close to 200 millisecond, my brain automatically jumps to maybe this is a nego delayed ACK problem, right? Because the counter is about 200 milliseconds for Windows unless you tune it, for example. So if I see numbers here that are consistent, close to 200, close to 100, close to 50, close to 75, then I suspect a systematic delay, okay? Because nothing in nature is works perfectly, right? There's no congestion that works perfectly at 50 millisecond intervals, 100 millisecond intervals, 200 millisecond intervals. But I do see just one, and there are other 20 millisecond delays, etc. So this one I want to look at, okay? So I make a note of, look at packet 18, I'll get to that in a second. The other thing that I do, of course, is looking at Tcp Analysis Flags, just to rule out, are there any TCP issues? And there are none. Okay, there are none. So there are no packet loss, everything's fine. But it's not fine because my throughput is not as I want, okay? So where am I? Where am I capturing? That's another thing that you need to look at, is because you need to set the frame of reference. Remember, retransmission looks different from the source, the sender, and the receiver, okay? The symptom of packet loss looks different from the sender and the receiver. How could that be? It's TCP, duplex. Because the sender sent it, the receiver didn't receive it. So you see previous packet missing here, but the sender doesn't see that because he sent it. There are no missing packets, he sent it. But he will see duplicate ACKs coming back and a retransmission, okay? So this is another quick way of saying, am I the sender, am I the receiver? By these types of symptoms. So, I know that was an easy thing to say, but I want you to picture it. This is why packet analysis is more art than science. Picture it in your head, okay? If you have to close your eyes, picture it. I'm the sender, and I send 10 packets worth of data, which means I'm free and clear. I sent it. There are no gaps in that, because I know I sent it. But it goes missing somewhere along before it gets to the receiver, so he's going to see the gap. You are not. Okay, so that picture looks different, and it's just a way of aiding setting the frame of where you're capturing by looking at those symptoms. So here, I see the SYN, I see the SYNAC sometime later, and then I see looking at the delta time. So here's, Big Bang, moment in time. I don't know where I am yet. Sometime later, 70 milliseconds later, I get an answer, SYNAC back, and then I immediately see an ACK back. So immediately I know I'm at 192.168. Okay, right? Everybody understands that, right? Because moment in time, I don't know where I am, Big Bang, I see a packet. Sometime later, I see a packet back, and then immediately I acknowledge. So I am very, very close to 192.168.0.1. All right. So the next thing you look at is am I doing things like window scaling? Am I doing SAC, etc.? And you can see here, multiply by 256. It's a pretty big window scaling factor. Maximum segment size of 1460, yet SAC is permitted. Here we have maximum segment size of 1340. We kind of knew that because down here you see the full size TCP length of 1340. And he says, yep, I'll do window scale of 6 multiplied by 64. And SAC is permitted, okay? So given that we have a pretty big window size, because I'm scaling by 256 in the other one, I'm scaling by 64 here, why am I not seeing the throughput that I'm seeing? So when you first troubleshoot, it's very easy to get wrapped around the axle on troubleshooting throughput issues by looking for packet loss, inefficiencies, etc. But one way that you can quickly visualize this is if you don't have a lot of experience, is because on paper, it looks okay if you're not that experienced. Meaning, let's just look at an example. Okay, let's scroll down to say here. All right. So I just picked some random packet somewhere in the middle, and I see two full 1340, 1340, and then a little straggler of 547 bytes. So this one is TCP length with all the headers. So this is IP with all the headers. Before, you couldn't add this TCP length as a column. That was added sometime in the recent update, okay? So how did I find that out? Because anything in brackets or parentheses is metadata that Wireshark is telling you, okay? So yes, there is actually a field for TCP length, but it's telling you, listen, this is TCP segment length, and I've exposed it because before it wasn't here, all right? So you have to actually go to the IP level and look at the IP length and add that as a column. Now, all you have to do is right-click here and say, apply as a column, okay? So if you see why do I have length and isn't this redundant? Yes, but again, my brain is trained to look at the length, and the TCP length is a bonus. That's why they're both there. Eventually, I'll wean myself off of it, but then the problem is what? Is the whole world TCP? No. If you troubleshoot multicast, there's no TCP, which means then I'll see nothing there, so I still need that IP length here. Anyway, so 1340, 1340, 547. So the first thing I do when I see numbers like that is I like to add them up, just to see if these are numbers that I should be worried about, okay? 1340, 1340 plus, and then the 547, 3227. So it's not 2048, it's not 4096, so maybe it's not a buffer issue, okay? You see what I did there? I added it up, the packet trains to see if I'm seeing 4096, etc. Okay? We're not out of the woods yet. We're not. I just picked one thing to see if I got lucky. All right. So let's keep looking at it. I see a delay here of 17 milliseconds. This is not a round-trip delay because round-trip delay is 70 milliseconds. So this is some additional delay. Why? Why was there a delay there? Okay. In other words, if I see 70, it may be something else, but I immediately chalk it up to round trip delay and move on. And I'll come back to it later if, but if it's 17 millisecond delay, followed by our big boy there, 190 millisecond delay, I'm interested, I'm curious, what's going on? So let's take a look. You always think you have plenty of time, but you don't. So let's take a look at what's going on here. So let's step back a few packets and walk this through, okay? I'm gonna hit Control M. I'm gonna hit Control M. Okay, well, Control M doesn't. Control M used to be Mark. Yeah, it is Control M. Why is it not working? Okay. Anyway, Control M doesn't work, so I'll follow that bug. So just so it's highlighted and I know where I left off, okay? I use Control T for time reference and Control M quite a bit when I'm troubleshooting, because the added benefit of Control T for time reference and Control M is that whatever filters you apply, it shows up in there too, so you never lose where you are. Okay, so just technique. You can use it, you don't have to use it. Again, my way or the highway, right? My way is better than your way, and vice versa. So if we pick a moment in time here, we can see that right away, I can see that this guy acknowledged packet number 9. I can cheat by looking at here, or I can cheat by looking at here. So this guy sent this much data, and this one is still, I sent this, which is different pattern than this, and this, okay? So it's not consistency of full size, small size. I have here 1340 and 708 and some delay there. So this application isn't streaming data, it doesn't look like. All right, so getting back to, stepping back here, 10.10 acknowledged, packet number 9. He didn't send anything, so this is a naked acknowledgement. Okay? He didn't have any data, so this is not a piggyback act, this is just a naked acknowledgement. So which one did he acknowledge? He acknowledged packet number 9. So this one, I'm capturing from 192.168. I sent this, pretty much I sent these 3 packets, bang, 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 and 22 milliseconds later, I see a reply coming back, and then I see this guy, me, sending additional data, and right away you have to ask yourself, hey, how can you still send data when you have an unacknowledged data out there? Okay? Right? I can, because a couple, Nagel rules, again, I don't want to get into the Nagel rules, but there are all these rules about when you can send, when you can't send, etc. So clearly here, from this point on, so here's, if I send some data, I get an acknowledgement, I continue after getting that acknowledgement of sending some additional data, bam, 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 I sent it. And this guy is acknowledging which one? Packet number 12. So there's obviously a lag in acknowledging it. It makes perfect sense. There's a 70 millisecond delay here. Okay? So what about this guy? Why was there a delay here before he sent? Were there any outstanding data to look at? So let's unmark this. So let's do analysis here. So here's naked acknowledgement, naked acknowledgement. So which one did he acknowledge? He acknowledged packet number 14. So this packet, number 16, acknowledged packet number 14. So as far as Amazon is concerned, Amazon acknowledged everything that I sent to it. Make sense? Long-winded way of saying, I sent Amazon a bunch of stuff, and Amazon said, I got it all. Okay? I know because this says right here, I acknowledge it to packet number 14. So this is Amazon's application level message saying, give me some more, or do something else, or give me the next chunk. I don't know, it's encrypted, I didn't bother, but this is an application asking you to send the next chunk, or etc. And off to the races we go, okay? So I acknowledge that you sent me the stuff, okay? Because if you send me something, I have to acknowledge it. And how long did that take? About 200 milliseconds. Why? Because it's a single packet, non-full size. I can't acknowledge it unless there's 2 packets. I'm Windows, so I'll acknowledge any 2 packets. So because he sent just one, I have no choice but to wait and acknowledge. I just wasted 200 milliseconds about, kind of inefficient. And then by the time the guy, I acknowledge that, I'm off to the races and say, all right, let me start. There was some thinking time involved here, 83 milliseconds, and here I am off to the races sending data. But it's also got push, push, push. Okay? I don't like that. So if you look at it visually, you'll see the classic buffer tearing problem. So let's zoom in. And you can use TCP Stevens graph, or you can use TCP trace. Okay. So if I zoom out a little bit, this is very typical. This is the pattern that you want to look for. Put this into your little toolkit, because this is buffer management. Application giving you not a whole lot of data. Why? Because each one of these dots represents data that's being sent by the packet. So if I click on a dot, it jumps to it in the background so you can kind of correlate what's happening. What you're seeing is this big jump here is the bucket size. And then we wait for it to be acknowledged, and here's the next bucket size worth of data. So here's a little bit of wait, next bucket size worth of data. Okay? So I don't care if you have a 100 gigabit network, your throughput can never exceed whatever the total is of this bucket size per act time here. Okay? Because you're not bound by congestion, you're not bound by bandwidth, you're not bound by serialization delay, you're bound by the application giving you chunks of data. And this is a very, very easy way of visualizing this. Okay? In the next session, when I show you some other examples, you'll see how the byte from the previous push can give you a hint on that. But here, it's meaningless because, so in other words, does everybody understand that before I get off this chart here? So this is the bucket size. Think of this as, yes, question?
Yeah, I don't understand why it's pushing the full NSS.
Yeah, so the question was, I'm very proud of myself, I'm repeating the question. The question was, why is it slapping a push bit on every single packet? And so let's just, pick one out at random here, packet number 151. And here's a push, here's a push, here's a push, and I don't know. The answer is I don't know, right? But it's problematic for me because if I looked at it from my default TCP view, you'll see here byte to previous push. And it never gets past 1340, so this is a big clue about inefficiency, okay? What I mean by that is, let me show you another trace file of a bulk transfer, okay? I'm gonna find one here. Let me just come up here and find one. Maybe there's one here. Okay, here we go. That push to byte, number of bytes since the push, is an important factor to identify because I went to Sharkfest again. Because here, if I sort by the number of bytes sent before previous push, what's my bucket size? 483,000 bytes. Okay? Just by having this flag that Carrie put in and checked in the code, I don't have to do this math manually anymore. Okay? And the way to get that is you look at the sequence number analysis here, and you'll see not only bytes in flight, but bytes seen since last flag. Okay? And so when you add that column, you can see here that this is my bucket size. In other words, if I were to sort back here, everything before this has no push bit. See that? This is just all which is exactly what I want to see because that's bulk transfer. Okay? So this testing. Angela. So this is why this byte to push is a very good indicator of looking at that bucket size, okay? And then if you look at the TCP analysis graph here, you can see, what do we see? Pretty good, right? So you can see this ramp up here is the bucket size about 480,000 bytes, which is awesome. And it wasn't like 8 or 10 packets. Oh, did we die? Thank you, sir. Which is awesome because that, if I zoom into there, you're going to see nothing but packets ties worth of data, okay? So number one, when you're doing application analysis and slow throughput issue, look for buffer tearing, but it's extremely common. Extremely common. So what we're going to do next session after 15 minutes, if you come back, is we're going to look at a couple of trace files. There's one that only has like 8 packets, but we're going to spend about 10 to 15 minutes on it. Okay? Question? The question is, am I using the TCP, TCP reassembly? No, I am not using TCP reassembly, and because I don't think I am, because if you right click here and go to protocol preference, you'll see that reassemble is not there, okay? And so Christian did a great session on TCP reassembly, but I'm at my time. So when we come back, for those of you that come back, we're going to look at some interesting trace files with just 6 or 7 packets that we can spend 15 minutes analyzing and a bunch of other slowness issues. All right? Thank you, everybody, and I'll see you in 15 minutes. If you want to check out other sessions, by all means, because I'm recording this, so this will be available on YouTube. Thanks, everybody.